Charles Kerby, who is pursuing a master's degree in civil engineering, where a lifelong interest in the building environment steered his study of civil engineering with a specialization in earthquake engineering. His fun fact, following his father's footsteps, he pursued both his bachelor's and master's degree in engineering as a Boilermaker. After graduating from Purdue, Charles plans to pursue his PhD in civil engineering at the University of Canterbury in Christchurch, New Zealand. Charles is an avid supporter of French soccer, Olympique Lyonnais? Lyonnais, all right. I don't speak French. I should have listened to our other speaker. Learn there, right? The title of his 3MT talk is Preserving Vulnerable Buildings, the Earthquake Response of a Novel Wood Infill.
One way to protect a vulnerable building from an earthquake is the construction of an infill. Now this retrofit practically describes itself. A weak area of the building frame is, well, filled in with another material to limit earthquake damages. Traditionally, infills are constructed from bricks and mortar, material combination that we know develops the high stiffness needed to reduce what earthquakes call drift demands, or the lateral distortions that a building must sustain during an earthquake to survive. But this traditional infill is also quite brittle. Its high stiffness can decay with little warning, and that can cause instabilities that could have dire consequences for the building or its inhabitants should an infill wall collapse. Because earthquake occurrences and intensities remain unpredictable, one question remains. Is there an alternate approach to infilling, one that can be both stiff and stable? In my research, I studied an alternate infilling approach in two parts. First, wood panels were constructed in test frames representing some of America's most vulnerable buildings. These wood panels were designed to develop the high stiffness needed to reduce drift demands. Second, clamps were tensioned about the columns of the frames, applying a confining pressure that prevented concrete from crumbling. This theoretically increased the peak distortions that the frames could sustain before brittle failure occurred. This alternate approach to infilling was tested against almost 100 simulations of the magnitude 7.0 earthquake that's familiarly known as the El Centro earthquake from California's Imperial Valley. I want to be clear, simulation in this context does not mean in a computer program. Each infill and frame was constructed and tested on Purdue University's 144 square foot earthquake simulation table at Bowen Laboratory. This table, as a fun fact, was the first in the world to accurately reproduce an earthquake ground motion in the late 1960s. When the dust from these simulations had settled, the novel approach to infilling of wooden clamps had exceeded all expectation. The wood panels successfully developed the high stiffness needed to reduce drift demand. But better yet, the combination of the wood panels and confining clamps allowed the novel infill to maintain the majority of its stiffness at distortions 10 times larger than the traditional masonry infill. Maintained stiffness allows otherwise vulnerable buildings to remain safe during intense ground motions. Allow me to summarize. When designing a building to resist an earthquake, stiffness means safety. The results of my experiment have shown that an alternate approach to infilling, a combination of wood paneling and confining clamps, better preserves the majority of high stiffness than the traditional masonry infill, and therefore could better preserve your safety.